Look at this club. It is roughly the size of your thumbnail. It is made of a mineralized material similar to bone, wrapped in layers of fibers wound in a helix, engineered to absorb and redistribute impact forces so completely that it does not crack or shatter despite being used as a hammer thousands of times over its owner's lifetime. It has a name, the dactyl club, and it belongs to a crustacean roughly 15 centimeters long that looks, at a glance, like something you might find in the seafood section of a supermarket. This club strikes at 23 meters per second, in under 3 milliseconds, delivering 1,500 newtons of force, roughly the impact of a .22 caliber bullet. It moves so fast that it vaporizes the water in front of it, creating cavitation bubbles that collapse with a shockwave, a flash of light, and temperatures briefly approaching the surface of the sun. If the shrimp misses, the shockwave still hits you. It has a two-stage weapon. It built this, voluntarily. Everything you were taught about what a small ocean animal is capable of was calibrated for creatures that follow the rules. The mantis shrimp has not been following them for 400 million years, predating dinosaurs, surviving every mass extinction, continuously refining a biology that, by any reasonable standard, belongs in something considerably more frightening. Scale the punch to a human body. The equivalent force would punch through reinforced concrete. The mantis shrimp does this underwater, where water resistance is 800 times greater than air, using not muscle is too slow, but a spring-loaded latch that compresses a saddle-shaped structure and releases it all at once in a movement faster than a human nerve impulse can register. It is not the strongest animal relative to size, or the fastest, or the most complex. What it has is a collection of systems: the punch, the eyes, the armor, the communication, each of which would individually be remarkable. Together, they make an animal evolution assembled specifically to be unreasonable. And the punch is the least interesting thing about it. Start with the weapon, because the weapon is where the engineering begins. The mantis shrimp has two types. Smashers carry the dactyl club, a mineralized hammer that cracks crabs, clams, and snails with repeated blows until the shell fails. Spearers carry a barbed limb edged with up to 17 spines, fired from a burrow the moment prey swims past. It waits, motionless, then fires once at a fish that had no warning and no chance. Both run on a biological spring latch, energy stored in a compressed saddle structure, released faster than muscle alone could achieve. The club does not swing. It is launched. Its outer surface is hydroxyapatite, the same mineral as bone. Behind it, fibers wound in a bouligand helix intercept cracks before they propagate, each layer stopping what the layer above could not. Thousands of full-force impacts. No failure. Researchers at UC Riverside used it as the template for helmets, vehicle armor, and aerospace panels. The mantis shrimp has been doing it, without a materials science department, for 400 million years. But the club is the part humans can conceptually follow. The eyes are where it leaves us behind. Humans have 3 photoreceptor types. The mantis shrimp has 12 to 16, yet it is worse at discriminating similar colors than we are. It is not building a richer picture. It processes color locally, each receptor returning a yes or no, trading discrimination for speed. It identifies what it sees almost instantaneously. It did not evolve a better vision, it evolved faster vision. And it runs its private communication on ultraviolet and polarized light, channels its predators cannot see, on a frequency they cannot intercept. The math says an animal this size should not be able to generate this force without destroying itself. The acceleration of the dactyl club strike, 10,400 times the force of gravity, is a number that belongs in artillery, not crustaceans. At that acceleration, the arm should break. It does not. The reason is the same Bouligand structure that protects the club from the impacts it delivers. The spiraling fiber matrix distributes the force of the strike through the arm itself, preventing any crack from propagating. It built a weapon that protects itself from itself. Full force, repeatedly, for its entire adult life. The arm does not wear out. Here is the detail that changes the scale of the whole thing. The cavitation bubbles briefly reach approximately 4,400 degrees Celsius. The surface of the sun is 5,500. For a fraction of a millisecond, a crustacean the length of your hand is producing temperatures within 1,000 degrees of the sun. It does this to open a clam, because a clam was nearby and it was hungry. To be fair, most of us just use a knife. Standard impact-resistant design operates on a trade-off. Hard materials resist deformation but crack under repeated stress. Soft materials absorb energy but deform permanently. The field has spent decades trying to combine both without sacrificing either. The mantis shrimp dactyl club solves this with 3 regions. A hard hydroxyapatite striking surface. Behind it, Bouligand-structured fibers rotating in a continuous helix, intercepting cracks at changing angles so none can follow a straight path. Around the sides, a compressive sleeve that further impedes propagation. Researchers replicating this architecture have produced composites that outperform existing designs in lab testing, applied in prototype helmet liners, aircraft panels, and body armor. The helix intercepts the crack. The compression contains it. The system holds. The mantis shrimp did not evolve this to help us build better armor. It evolved to eat shellfish. We reverse-engineered a weapon system from a crustacean's lunch equipment, and the lunch equipment is still better. The mantis shrimp is 15 centimeters long. It lives in a burrow on a coral reef. It eats crabs. It has no awareness of the US military, of materials science departments, of the decades of research its appendages have generated. It is not remarkable to itself. It is simply doing what 400 million years of evolution produced the most efficient possible version of. It is the most heavily studied crustacean in materials science, fluid dynamics, optics, and neuroscience simultaneously, and it has never once applied for a grant. You are the version of life that looks at a creature eating a clam and asks what it can teach you. The mantis shrimp is the version that just eats the clam. Both approaches, it turns out, are working. But if a 15-centimeter crustacean has already solved problems in materials science, optics, and fluid dynamics that took us decades to identify, what else is sitting on a reef somewhere, casually doing something we have not thought to ask about yet? Because the mantis shrimp is one of over 450 known stomatopod species, most have been observed but not studied at this level of detail. The peacock mantis shrimp is the famous one, the one in the papers, the one in the materials labs. The others are still out there, in their burrows, running biological systems we have not examined yet. The ocean is not withholding its secrets. It is displaying them. We just keep looking at the wrong things.